Welcome to the Subaru Motor channel. This channel provides easy-to-understand explanations of car mechanisms. Subaru has finally introduced hybrid vehicles to the world. Fuel efficiency has long been considered a weakness of Subaru vehicles, but this should greatly improve that. Subaru vehicles feature a uniquely distinctive powertrain layout, with a longitudinally mounted boxer engine, a transmission that integrates a transfer case and front differential, and a mechanical AWD system with a propeller shaft. Therefore, their transmission also has a unique structure, which, in addition to the gearbox, includes a transfer gear, AWD coupling to distribute power to the front and rear wheels, and a front differential. Needless to say, the hybrid system must also be equipped with them. For these reasons, although this hybrid is based on Toyota's hybrid technology, it was independently developed by Subaru. Before we discuss the hybrid system, let's take a look at Subaru's unique transmission structure. This is the configuration of the CVT, continuously variable transmission, commonly used by Subaru. The output from the boxer engine is input into the torque converter. After the torque converter, there is a forward and reverse switching device utilizing a double-pinion planetary gear. The output from the forward and reverse switching device is transmitted to the primary pulley, which, together with the secondary pulley and chain, increase or decrease the rotational speed. The output from the secondary pulley is distributed to the front and rear wheels via the transfer gear. The output to the front wheels is directly transmitted to the front differential, while the output to the rear wheels is transmitted to the propeller shaft through a multi-plate hydraulic clutch for AWD torque distribution. The hybrid system is also packaged in a layout similar to that of the CVT. The system consists of a primary reduction gear, the first electric motor, a planetary gear-type power split device, a transfer gear, a front differential and an AWD coupling, a motor reduction gear, the second electric motor, a traction inverter, and a hybrid battery. Before going into details, we will first learn briefly about the operation of planetary gears. A planetary gear consists of three main components: an internal gear, a sun gear, and a planetary carrier, along with planetary pinions that rotate as a unit with the planetary carrier. By assigning input, output, and fixed roles to these three components, it is possible to increase speed, reduce speed, or reverse rotation. Step-type automatic transmission shift gears using this function of the planetary gear set, whereas the Subaru hybrid system utilizes a different function. We will cover that later. So for now, just remember that the planetary gear set shifts using three elements. In the Subaru hybrid system, the two electric motors switch roles between generating power and producing output depending on the situation. For this reason, the electric motors are called MG, motor generator, and the two electric motors are named MG1 and MG2, respectively. The output from the engine is reduced by the primary reduction gear, and the reduction gear shaft is connected to the planetary carrier. MG1 is connected to the sun gear. MG1 and the MG1 shaft are hollow, allowing the reduction gear shaft to pass through their interior. The internal gear is connected to the transfer gear, which distributes driving force to the front and rear wheels. One output shaft from the transfer gear is connected to the front differential, while the other is connected to the AWD coupling, which controls the distribution of driving force between the front and rear wheels. The shaft to the front differential is connected to MG2 via the motor reduction gear. MG2 and the MG2 shaft are hollow, allowing the shaft that connects the transfer gear and the AWD coupling to pass through their interior. Let's take a look at how the hybrid system operates under various driving conditions. During acceleration from a stop, the vehicle is driven solely by the output of MG2. At this time, since the engine is off, the planetary carrier is stationary, while the planetary pinions and sun gear rotate freely. When the vehicle speed reaches a certain level, the engine starts. For engine startup, MG1 operates as a starter motor and rotates the engine via the planetary gear. When driving with the engine alone, the engine output is input to the planetary carrier and output from the internal gear. At this time, the planetary gear functions as a continuously variable transmission, CVT, allowing the vehicle speed to change while keeping the engine speed constant. The planetary carrier is connected to the engine, the sun gear to MG1, and the internal gear to the wheel. MG1 operates as a generator and alters the rotational resistance of the sun gear. Increasing the power output of MG1 raises the rotational resistance of the sun gear, making it harder to rotate. Decreasing the power output reduces the load on MG1, which also lowers the rotational resistance of the sun gear. The engine speed is constant now. The power generation of MG1 reaches its maximum, and the rotational resistance of the sun gear increases to its highest level, causing it to stop. At this time, the internal gear rotates faster than the planetary carrier. In other words, it results in a top gear state, where the output rotational speed is higher than the engine speed. Lowering the power output of MG1 increases the rotational speed of the sun gear. This causes the rotational speed of the internal gear to decrease, which is the low gear state. In this way, by continuously varying the load on MG1, the vehicle speed can be changed while keeping the engine speed constant. By combining this feature with an engine that prioritizes fuel efficiency over output performance, and shifting within the engine's most efficient speed range, fuel consumption can be significantly reduced. During rapid acceleration, the engine and MG2 combine their output to generate strong driving force. During deceleration, MG2 operates as a generator, and its resistance is used as braking force. This function is called regenerative braking. The traction inverter controls motor generators. It is equipped with 6 power transistors, and the inverter control unit switches them to convert the battery's DC electricity into AC electricity, driving the 3-phase AC motor. The video, Deep Dive into Toyota Hybrid System, explains the details of traction inverter operation and how regenerative braking is controlled when the battery is fully charged. If you're interested, please check it out. The link is available in the description. In hybrid AWD vehicles based on FWD system, the rear wheels are typically driven by a dedicated electric motor. However, Subaru chose a mechanical AWD system with a propeller shaft. According to Subaru engineers, they chose it for 2 reasons: responsiveness and ensuring rear-wheel drive force. First, let's consider responsiveness. Suppose the front wheels of a rear motor AWD vehicle are on ice. When the driver depresses the accelerator pedal, the front tires slip. Since the VDC control unit constantly monitors the rotational speed of each wheel, it detects slippage when there is a difference between the front and rear wheel speeds. The control unit calculates the appropriate drive force for the rear wheels based on factors such as the difference in rotational speed and the accelerator pedal input. The VDC control unit transmits signals for rear motor drive activation and front motor drive force reduction to the traction inverter control unit via the CAN line. The traction inverter control unit supplies power to the rear motor, while reducing the rotational speed of the front motor. The vehicle starts moving. This series of operations takes place in a very short time. However, it is not 0 seconds. In mechanical AWD vehicles, driving force is always transmitted to all four wheels. The distribution ratio for the hybrid model has not been disclosed, but in the CVT model, the driving force is distributed as 60% to the front and 40% to the rear. Even if the front tires slip, there is no delay, and the rear tires can still move the vehicle forward. Subsequently, if necessary, the clutch pressure of the AWD coupling is controlled, similar to the rear motor system, to increase the driving force to the rear wheels. Next, let's consider ensuring rear-wheel drive force. The hybrid model of the Toyota RAV4 is equipped with a powerful rear motor that delivers a maximum torque of 121 Nm. According to Subaru engineers, that is completely sufficient for typical snowy roads. However, in extremely challenging conditions, such as a steep uphill where three wheels are slipping, the vehicle must move forward with the driving force of just one wheel. In such cases, the torque from the rear motor alone is insufficient. The engine in Subaru's hybrid system produces a maximum torque of 209 Nm, while MG2 delivers 270 Nm. However, the total system torque has not been disclosed. For explanation purposes, let's assume the total maximum torque of this system is 400 Nm. The front two tires and the right rear tire are slipping. In the rear motor AWD vehicle, the VDC applies braking to the right rear wheel, so 121 Nm is applied to the left rear wheel. In a mechanical AWD vehicle, with the AWD coupling fully locked and the VDC applying braking to the right rear wheel, 200 Nm can be applied to the left rear wheel. As mentioned earlier, Subaru engineers say that rear motor AWD systems pose no issues on typical snowy roads. However, in extremely harsh conditions, such as severe muddy or icy uphill roads, mechanical AWD systems would demonstrate a significant advantage. One more thing, Subaru Hybrid AWD system has a major distinguishing feature. For the first time in the history of Subaru's full-time AWD, which began in 1989, this system completely cuts off drive power to the rear wheels. The AWD coupling in CVT vehicles is hydraulically controlled, adjusting the clutch engagement force to regulate the torque transmitted to the rear wheels. In CVTs, a high-capacity hydraulic pump is required to generate hydraulic pressure for controlling the transmission mechanism, and this pressure is also used for AWD coupling control. This channel have a detailed video explaining how CVTs work. If you're interested, be sure to check it out. The link is in the description. The Subaru hybrid system is equipped with an oil pump for oil circulation to lubricate and cool the motor, but it does not generate hydraulic pressure. Therefore, this system does not have the hydraulic pressure to operate the AWD coupling. For this reason, the Subaru hybrid system uses an electromagnetic AWD coupling instead of a hydraulically controlled multi-plate clutch. The adoption of this coupling has made it possible to completely cut off drive power to the rear wheels. Surprisingly, this Subaru switches to front-wheel drive depending on the conditions. But Subaru fans, there's no need to worry. This system is based on a different philosophy compared to other on-demand AWD systems. A typical FWD-based on-demand AWD vehicle operates in front-wheel drive under normal driving conditions, whereas Subaru hybrid vehicles constantly apply driving force to all four wheels. On-demand AWD vehicles transfer driving force to the rear wheels only when slippage occurs. Subaru hybrid vehicles always deliver power to all wheels, and the AWD coupling cuts power to the rear wheels only when the system determines that four-wheel drive is not necessary. Even in front-wheel drive mode, drive power is instantly distributed to the rear wheels in response to steering inputs or changing road conditions. Therefore, on rough or snowy roads, it performs just like the previous full-time AWD, while improving fuel efficiency during highway driving. Subaru classifies the FB25 engine as a Miller cycle engine. Miller cycle engines create a difference between the intake and expansion strokes by delaying the closing timing of the intake valve. This type of engines offer better fuel efficiency than engines of the same displacement, but has lower power output. Let's compare the FB25D engine, designed for conventional gasoline-powered vehicles, with the FB25 engine for hybrid vehicles. Both engines have the same bore and stroke of 94 and 90 mm. The FB25D produces 136 kilowatts and 239 newton meters, while the FB25 generates 118 kilowatts and 209 newton meters. We can see that the FB25 has lower output, which indicates that the engine prioritizes fuel efficiency over high output. In the Subaru Hybrid System, the high fuel efficiency of this engine is fully utilized, while its low power output is compensated by the assistance of an electric motor, resulting in excellent overall fuel economy. This channel offers a detailed video explaining Miller cycle engines. If you're interested, be sure to check it out. The link is in the description. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.